So our project was titled "The Search for Exoplanets in the Open Clusters Messier and Koposov 62, using a novel large-scale photometric algorithm for the crippled Kepler mission." But first we'll present a little bit of our citizen science journey and where that has led us. So we started astronomy when we were around 6. Our father had a 9.25-inch telescope, and he had always wanted to use that. And he told us if we pointed 10 objects with a smaller telescope, we'd get to use his larger telescope. So he bought us a small 4.5-inch Starblast telescope, and pretty soon we had pointed at many more than 10 objects, and we were very, very passionate about astronomy. And this is our 4.5-inch Starblast. We still have that Starblast, it's in the center. But we've upgraded. Yeah. So that's our 16-inch in the corner for visual. And we also have an astro imaging setup in the other side that we use often to take images. And so in the 6th grade, we did our first science fair. And that was in the field of plant biology. And so we submitted our science fair to the county science fair. And contrary to our expectations, it was actually very, very competitive. There were projects ranging from model volcanoes all the way to cutting-edge cancer research. But more importantly, we found that we could present our research to experts in the field, get advice, and be inspired to continue our work. So yeah, in 7th grade, we had a seed for an idea to do another science fair. Over the summer, by now we were passionate astronomers and we regularly attended star parties. And at one such star party, an amateur astronomer named Dave Majors asked us to look through his telescope. And when we looked through, there was a faint, dim red star in the telescope. And this by itself wasn't very interesting. But he told us that this star, called R Corona Borealis, was actually a variable star. And over time it changed. So only a few months ago, it was bright enough to be visible to the unaided eye. And this fascinated us because we were used to astronomical phenomena changing over time scales of millions and billions of years, not over a few months or even on our lifetime. So we did a little bit of background research into this, and we found that actually with a regular camera, like the one many of you might be having right now, and a tracking tripod, we could actually study these stars by performing photometry. So we could essentially look at the brightness of these stars over time. So that's what we did. Every night for the next 6 months, which it was actually clear, we went out, we set up our camera and our tripod, and we took pictures of 2 variable stars, Beta Lyra and Delta Cephei. And at the end of those 6 months, we converted those images into graphs of brightness over time. And we were actually really excited to find that we could both see the primary and secondary minima that you would expect to see if you have 2 stars orbiting around each other. And also we were able to see the pulsating pattern of a star that's unstable and pulsating. So that was very exciting, and this spurred us to continue our research. So the natural progression for us was towards exoplanet research. And so as I mentioned earlier, we were avid astrophotographers. We, at one point we took an image of this object called the Dumbbell Nebula. And while we were doing our background research, we found that we had inadvertently captured the host star of an exoplanet, which is HD 189733. And so we decided to see if we could study this further. So with the same equipment that we used to capture this image, we studied we took several images over the night of the exoplanet host HD 189733, and tried to see if we could capture a transit, the dip in brightness as a planet crosses the face of the star. And once we processed our data, we were amazed to find that we had actually captured the transit, which is quite spectacular. And we were also amazed by how much we could find just by the light that's coming out of the star. We could find some characteristics about the exoplanet. We could also find possibly how it formed. We continued this research into our 9th grade year, and where we studied the characteristics of exoplanets and how they formed and other things like that. So all of these years, from 6th, 7th, 8th, and 9th grade, we had been doing some projects, and we had been doing science fairs, and we had been presenting our projects at the county state, and even in the 7th grade, we made it to the national level science fair. But it had always been a dream for us to attend the Intel International Science and Engineering Fair. And I'm happy to say that in 10th grade, we finally were able to make it to ISET. So now I'll present the project that allowed us to make it to ISET.
You've got the first right.
Yeah, so yeah.
So these are they won the state, the county, which is the Synopsis Valley Championship. They won the grand prize, and then that allowed them to go to California State, which they won the first prize. And that's kind of enables them to go into ISET, which is 72 countries participate in science fairs all over the world.
So yeah, again, as amateur astrophotographers, we had taken a lot of images of objects such as this, the Heart Nebula in Cassiopeia. And what we noticed is that a lot of these star-forming regions, which have nebulae, gas and dust essentially, also had open clusters at their cores. And this was very intriguing to us, and upon further research, we found that all stars actually form clusters. And over time, these clusters can either dissipate and just form regular isolated stars, or they can stick together and form what's called an open cluster. Now, the Kepler Space Telescope, which was launched in, I think, 2007, was instrumental in finding exoplanets. And out of the 5,000 exoplanets that Kepler has found, that have been found, over 4,000 planet candidates have been found by Kepler. And all of these planet candidates have been found around isolated stars. So what we wondered was, can exoplanets exist within open clusters? And furthermore, if they do exist within open clusters, what is their prevalence compared to exoplanets outside a cluster? So we also asked 2 more questions, which Shishir will come to in the next slide.
So we were quite shocked to hear when Kepler failed in 2012. So Kepler had originally been pointing in one location of the sky for 5 years almost. And then when it failed, it lost its ability to point stably. So the scientists at NASA actually engineered an ingenious salvage mission called K2, which used the pressure of the light from the sun in order to stabilize the spacecraft and allow limited observations to continue. So with this salvaged Kepler mission, we realized we could actually observe the open clusters that we were interested in observing, because this new Kepler mission was now pointing at different areas of the sky. And the engineering test of the salvaged Kepler mission called K2 was going to be pointing at 2 open clusters. One was called Messier 35, and the other is called Koposov 62. And we thought we could study these open clusters. So we immediately encountered some challenges. First of all, the original Kepler mission had sent down to Earth graphs of the star's brightness over time that people could look for transits in and find exoplanets. Unfortunately, this new Kepler mission, this K2 mission, sent down to Earth images, and there was no algorithm that could convert those into light curves. And second of all, there was the problem of, especially the open clusters that we were studying, the fields are extremely crowded, and it's difficult to isolate one star from the background and the neighboring stars in order to make measurements.
And so, for example, yeah, this is an example of stellar overcrowding that you see in a cluster, and you can see that it's very hard to even a human finds it very difficult to tell where one star, where the boundaries of a star lies.
And the other problem is the new Kepler mission was not as precise in terms of pointing as the original Kepler mission was. And this is a big problem because I recently heard an analogy that displays how much precision you need in order to be able to get a transit of an Earth-sized exoplanet. If you were in Los Angeles and you were observing the Empire State Building through a telescope and all of the lights were on and one person closed their shutter 1 inch down, that's the precision that you need to be able to achieve in order to detect a transit. So any amount of noise, including that ones caused by the motion of the spacecraft, could contaminate your data and prevent you from getting a transit. So eventually we worked, the biggest problem that we had though was we had no knowledge of computer programming in order to actually make this algorithm. So we started out by downloading some software into our computer and messing around with the data, experimenting a bit, and trying to see what we could do with with the data to try and create an algorithm. And over time, we learned the computer programming, computer program that we were planning to use, which is called Python, and we started to make our algorithm. So our final algorithm started out with the K2 images. The K2 took one image every 30 minutes for 85 days at a stretch. So there were actually literally millions of images that the K2 mission was downloading. So we took each one of those images. We ran an algorithm that would find stars in each of the images. And then from there, we had to address the problem of isolating each one of the stars individually so we can study them. So we created a new way to mask off the stars from the background and the neighboring stars in order to study only the star that we were interested in. And we did this for every single star in every single star field. And we performed this. We extracted the brightness from each of these masks and formed graphs of the light curve, we formed graphs of the star's brightness over time. And we did this for every single star. Finally, we applied some processes to the light curve to reduce the amount of noise caused by the wobble of the spacecraft, and some other processes that would essentially clean up the graphs. So we studied a total of around 620 stars in the open cluster and an equal sample of 620 stars in an isolated star field so that we could compare between the two.
So yeah, we were actually very excited to find that we had discovered from this 4 new exoplanet candidates. So now I'll show you the light curves of these exoplanet candidates that we found. I should also mention that all of the candidates we found were in the open cluster, and none of them were in the isolated star field. So this was also very interesting. So first, I should say that, that the top graph displays the raw light curve, so essentially what our algorithm outputted. And the bottom light curve, all of these, if we are looking at an exoplanet, we would expect the dips in brightness to be of all the same size and shape. So what we can do is we can actually sort of stack these transits on top of each other to get one average transit, which is far more precise. And using this, we could actually find a number of characteristics about the exoplanet. For example, this exoplanet has a roughly 7-day period, and it's likely to be a large Jupiter-sized exoplanet that orbits very, very close into its host star. So what's called a hot Jupiter type exoplanet. And this exoplanet is very interesting because it's actually a very short period. So it has a period of under 1 day, and its dip in brightness is what you would expect of a mini Neptune. So it's a little bit smaller than Neptune, and it also orbits very, very close to its host star. And both of these previous light curves that I showed you were in Messier 35. And this exoplanet is in Koposov 62, this exoplanet candidate. And this exoplanet candidate is also in Koposov 62. So here's a graph or a data table that essentially summarizes the characteristics of these exoplanet candidates. So you can see that all of the exoplanets have very, very short periods. And that's actually because the K2 telescope is not able to look at one field of view for 5 years as the original Kepler mission did. It's looking at one field of view for just 85 days and moving on. And furthermore, you actually need to be able to get 3 transits in order to be able to confirm that that this is an exoplanet and not just a random occurrence that would cause a dip in brightness. So 85 divided by 3 is the maximum period of an exoplanet that you can find. And yeah, also all of them orbit very close into their host star, and that's also that's a direct I guess it's a direct consequence of the amount of time that we're looking at the star field of view. So some of you noticed in the previous slide that all of the exoplanets we found were actually in the open cluster. And this was completely unexpected. What we had expected originally was that we would find very few or no exoplanets in the open cluster,
because they would be ejected by the gravitational violence inside the open cluster. What we ended up finding, however, was that there were far more exoplanets in the open clusters than outside the open clusters. And we came up with some possible hypotheses as to why this could be. But first of all, we know that exoplanets do probably exist in open clusters. We cannot conclude with certainty what the prevalence of exoplanets in open clusters are, because we didn't have a very large sample size. But the data suggests that it's definitely more prevalent. And the explanation we came up for this would be that in an open cluster, an exoplanet, while it's forming, exoplanets, when they're forming, are often ejected. So in an open cluster, this ejection once the exoplanet is ejected, it'll go off a ways, and then it might be recaptured by another star very nearby in the open cluster. However, in an isolated star group, if these exoplanets were ejected, they'd be ejected off into space, and they would not be recaptured. So the net effect is, in an open cluster, you end up seeing a lot more exoplanets than you do outside an open cluster. And so we're looking to test this hypothesis. It is actually testable. If we find exoplanets with very weird-looking orbits, that would suggest that they've been recaptured. And so right now we're working on trying to find out whether this is true or not. And so in the future, I mentioned we were going to try and see if this recapture hypothesis is plausible. We've already started by performing some simple simulations to test whether this might be true, and many of the simulations indicate that it's quite possible. And second of all, this is just the engineering test of the new Kepler mission. There are still many more missions. In fact, I think there are 13 campaigns that this new Kepler mission is going to be going through. So, and each one of those is a different field. And as a consequence, there are many very large open clusters it will be looking at. And our algorithm will work on all of those open clusters. So we're excited to be able to study more open clusters, increase the amount of data we've been collecting, and to try and solidify our conclusions. And in addition, we can also answer some more questions, like how does the age of an open cluster affect how many planets we find inside? And so as a consequence, I mentioned earlier, we got to go to the International Science and Engineering Fair, and we won a prize there that allowed us to go to the Large Hadron Collider in Switzerland. And so this is us with the in front of the one of the detectors at the Large Hadron Collider.
This one's called CMS. It's the Compact Muon Solenoid. So,
and yeah, we also got the opportunity to present our research to the Kepler team at NASA, which was extremely exciting. And actually, some of the Kepler team expressed an interest in helping us out. So we're now working with the Kepler team, and we're getting help from them. Most recently, I'm very excited to say one of the exoplanets we discovered was observed by the Keck telescope in Hawaii, and we got some follow-ups, and we're waiting for the data to come in. But as soon as it comes in, we'll analyze it and find out whether some more about this, some more characteristics.
Yeah. So I should also mention that the data that we collected from Keck recently was not the normal use of a follow-up. It was actually first, in order to confirm that this is indeed an exoplanet in the open cluster, we have to verify that the exoplanet is indeed in the open cluster. So first, we got a very short amount of time on the Keck telescope to be able to confirm that yes, this exoplanet is indeed in the open cluster. But now we also need to find out whether it really is an exoplanet in the first place. So most likely that will have to be done through a radial velocity study. So that's what we're looking into doing as well in the future. And yeah, I should also say that we've been living in the Bay Area for our practically our whole life, but we've never quite got to visit the Lick Observatory yet. So this is our first time at the Lick Observatory, and it's been an amazing experience so far, and I'm sure it'll continue to be an amazing experience. So thank you very much for this visit, and thank you.
I want to say thank you for coming up and and presenting your research is absolutely fascinating, and you know, we do a lot of exoplanet research up here at Lick Observatory, so it's nice to see some fresh young faces. Yes?
I'd like to suggest that for your Doppler confirmation, maybe you should get some time on the ATM telescope.
Yeah, that would be amazing.
Yeah. We might be able to hook you up with the right people with that. Yes, certainly. I work with Jeff Marcy, who runs the APF telescope. So who knows? There might be possibilities there.
Certainly. There are four candidates. So NASA team felt that the first one looks more likely, more likely to confirm it, kind of exoplanet. So
and that's also bright. The first one is also bright enough for a radio velocity of all electricity.
Okay.
So that's the one we're looking at right now.
Yeah. Great. That's fascinating. Any questions?
I was worrying about that mask you made for the star. Did you have to make those by hand, or were you able to generate those from some characterization of the piece?
Yeah. Our algorithm, we actually developed a new way to intelligently mask them. So because we were analyzing so many stars, we couldn't go in and mask each one of them by hand. So we found a way to fairly intelligently mask them according to the brightness of the star.
Okay.
Can I just say, wow? All of us in this room have seen a lot of presentations over the years, and from people who have, you know, PhDs in astrophysics and have been doing research for, you know, probably longer than you guys have been alive. And this is one of the most interesting presentations that I've had a chance to see up here.
I'll just second that and remind you guys, if you may not know this, but when you go to graduate school or something like that, you go to a lot of conferences, most talks are just horrible. Most people are terrible. And you guys are way ahead of that curve already. So that will serve you well. I mean, most talks are so unclear.